Now let us add one more influence, namely gravity. We will study how objects move under both gravity and an initial motion state. The experimental setup that we will use is simply a stone and a tower. We will drop the stone from the tower and then plot the position versus time of the stone. We make sure that all other influences are negligible. The stone encounters little air resistance as long as its velocity relative to air is not too high. The stone is not in contact with other solid objects as it is falling, thus, there are no normal reaction forces or friction forces. The stone has no electric charge, thus, there are no electric forces. The stone is not magnetic, thus, there are no magnetic forces. Next we will use two physical observations to derive equations that will enable us to calculate the position, velocity and acceleration of a falling object. First we will observe objects with different masses, that are falling. And second we will observe the time it takes for an object to fall from different elevations, and we will derive an equation to predict this time. Legend has it that Galileo conducted his experiments by dropping objects off of the Leaning Tower of Pisa. As early as 55 BCE, probably even earlier, scientists observed that if we could neglect air resistance, then, if we drop a large rock and a small rock at the same time from a certain elevation, both rocks will reach the ground at the same time. In fact, in the absence of air, if we drop a feather and a rock from a certain elevation at the same time, then they will both reach the ground at the same time. Even though the large rock, the small rock, and the feather all have different masses, they all reach the ground at the same time. This principle can be generally stated as, bodies of different masses that fall from rest, travel the same distance in the same time. For objects falling in air, we can neglect air resistance, if the following conditions are met. The object has a much higher density than air. The object has a relatively small attack surface area through which it is falling. The maximum velocity of the object relative to the air is small. These conditions will be quantified later in the course. Let's measure the time it takes for an object to fall a certain distance, from rest. So let's take a rock, and drop it from different elevations. And for each elevation we will measure the time it takes to reach the ground. We will record the time and elevation in the shown table. And plot each point on the graph below. With elevation on the y-axis. And time on the x-axis. First, we know that at an elevation of 0 meters, the time it takes for the object to reach the ground is 0 seconds, since the object is already on the ground. At an elevation of 1 meter, we let the object fall, and observe that the object takes about 0.452 seconds to reach the ground. At an elevation of 2 meters, the object takes 0.639 seconds to reach the ground. At an elevation of 4 meters, the object takes 0.903 seconds to reach the ground. We can continue taking time measurements for other values of the elevation. 6, 8, 10, 14, 16, and finally 20 meters. Let's connect these points. Now we can use this plot to predict the time it takes for an object to reach the ground, at other values of elevation. For example, at an elevation of 3 meters. We can look at the graph and see that the object will take approximately 0.782 seconds to reach the ground. Alternatively, if we know the time it took for the object to reach the ground, we can use this graph to predict the initial elevation of the object. For example, for a time of 1.5 seconds, we see from the graph that the initial elevation of the object is approximately 11.025 meters. Let's try to write a mathematical equation that will fit the points in the line graph that we saw in the previous slide. This equation can then be directly used for predicting the elevation if we know the time taken to reach the ground. And then we will no longer need the graph. We can write this relation as x is equal to f of t, where x is the elevation of the rock above the ground, and t is the time the object takes to reach the ground. This graph looks like a parabola. Therefore let's propose the equation, x is equal to c2 times t squared, plus c1 times t, plus c0. At an elevation of 0, the time taken is 0. And so substituting 0 for x and t, into the above equation, we get 0 is equal to 0 plus 0 plus c0, which implies that c0 is equal to 0. As found in the previous slide, at an elevation of 1 meter, the time taken is 0.452 seconds, which implies that 1 is equal to 0.452 squared, or 0.204, times c2, plus 0.452 times c1. And similarly at an elevation of 2 meters, the time taken is 0.639 seconds, which implies that 2 is equal to 0.639 squared, or 0.408, times c2, plus 0.639 times c1. Equations 1 and 2 are two equations with two unknowns, c1 and c2. Now let's solve these two equations for c2 and c1. Multiplying the first equation through by 0.408, we get the highlighted equation. And multiplying the second equation through by minus 0.204, we get the next highlighted equation. Now adding these two equations together, we get 0.408 minus 0.048, or 0, is equal to 0.083 minus 0.083, or 0, times c2, plus 0.184 minus 0.130, or 0.054 times c1, which implies that c1 is 0. So now substituting 0 for c1, into the first equation, we get c2 is equal to 1 over 0.204, which is approximately 4.9. So we have x is equal to 4.9 times t squared. The relation given by equation 3 is valid for any object of any mass, if air resistance can be neglected. The general observation, then, is that if we drop an object for which air resistance can be neglected, from a certain elevation in meters, the time taken, in seconds, for the object to reach the ground, is given by equation 3. Note that this formula is valid only for when the initial position of the object is a rest position, i.e. the velocity and acceleration are both 0. Note too that we can easily invert this equation, to get the time it takes for the object to fall from a certain elevation. We can rewrite this equation, as t is equal to the square root of x over 4.9. Let's check and see if the equation that we derived in the last slide agrees with what we have observed. Let's take for example, t equals 0.903. From the equation, we have x is equal to 4.9 asterisk 0.903 squared, which is approximately 4. And thus agrees with what we previously observed. Let's check another one. For t is equal to 1.106. We have 4.9 times 1.106 squared, which is approximately 6. And again, it agrees with what we previously observed. If we check all the points in the table, we will find that they all agree with this equation. We can perform this experiment in another way, by using the same tower, along with a high-speed camera. We will let the object drop from a certain height. Then using the high-speed camera, we will take snapshots at equal time intervals of the object as it falls. If the frame rate of the camera is 10 frames per second, and we take a snapshot every frame, then in 2 seconds we will have 20 frames. We will record each frame in a table, along with the time, in seconds, and the distance, in meters, that the object has fallen. We will also plot each point in the shown graph. At frame 0, the time is equal to 0, and when the object is released, it is still at the same height. At frame 1, after 0.1 seconds, we observe that the object has dropped 0.049 meters. At frame 2, after 0.2 seconds, the object has dropped 0.196 meters. At frame 3, after 0.3 seconds, the object has dropped 0.441 meters. We can continue until we reach frame 20, after 2 seconds, and the object has dropped 19.6 meters. Let's connect the points in the graph. Finally, let's confirm that the relation we derived from the previous experiment match these readings. The equation that we obtained previously is x is equal to 4.9 times t squared, where x is the distance in meters that the object has fallen, and t is the time in seconds. So let's take for example frame number 5, at time 0.5 seconds. Substituting 0.5 for t in the above equation, we get x is equal to 4.9 times 0.5 squared, which is equal to 1.225, which agrees with our observed result. Let's take another example, frame number 10, at time 1 second. Substituting 1 for t in the above equation, we get x is equal to 4.9 times 1 squared, which is equal to 4.9. And this also agrees with our observed result. If we do this for each point in the table, we will find that they all agree with the equation x is equal to 4.9 t squared. In this section we have made the following two observations. 1. Bodies of different masses that fall from rest travel the same distance in the same time. 2. If we drop an object, for which air resistance can be neglected, from a certain elevation x, given in meters, the time t, in seconds, that it takes for the object to reach the ground, is given by the equation x is equal to 4.9 times t squared. Given the relation that we derived previously, x of t is equal to c2 times t squared, where c2 is equal to 4.9. Let's derive the equations for instantaneous velocity and instantaneous acceleration. For instantaneous velocity, v of t is equal to dx dt. And so substituting the expression for x from the previous equation, we get the derivative of c2 times t squared, which is 2 times c2 times t. The equation for acceleration is a of t is equal to dv dt. And so substituting the expression for v from the above equation, we have the derivative of 2 times c2 times t, which is equal to 2 times c2. Since c2 is equal to 4.9, then a of t is equal to 2 times 4.9, which is equal to 9.8. This means that for falling bodies, if we can neglect air resistance, the acceleration is constant and is equal to 9.8 meters per second squared. This is the value of acceleration at sea level on Earth, and we call this quantity the Earth's gravitational acceleration at sea level. It is usually denoted by the small letter g. And so we have g is equal to 2 times c2, which is equal to 9.8. Replacing 2 times c2 by g in the acceleration equation, we can rewrite the acceleration equation as a of t is equal to g. And similarly replacing 2 times c2 by g in the velocity equation, we can rewrite the velocity equation as v of t is equal to g times t. And finally replacing c2 by g over 2 in the position equation. The position equation can be rewritten as x of t is equal to 1/2 of g times t squared. Therefore, if an object is falling vertically, without any horizontal motion, we can use the constant acceleration 1D kinematic relations, with a of t equals g To calculate the velocity and position of the object. Note that the sign of g depends on the orientation of the x-axis. If the x-axis is pointing down, then the sign of g is positive. On the other hand, if the x-axis is pointing up, then the sign of g is negative. At the end of the last Apollo 15 moonwalk, Commander David Scott performed a live experiment from the Moon's surface. He dropped a 1.32 kg aluminum geological hammer and a 0.03 kg falcon feather at the same time, from the same height, of around 1.25 meters. Because they were essentially in a vacuum, there was no air resistance, and the feather was observed to fall at the same rate as the hammer. They both reached the ground at the same time, just as Galileo's theory predicted. Next we will watch this movie. And then we will calculate the gravity on the Moon's surface. And then experimentally verify that the motion of objects on the Moon follows the same law as motions of objects on the Earth.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the Moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Which proves that Mr. Galileo was correct in his findings.
Now let's calculate the gravity on the Moon's surface. To do this, we need the time the object takes to fall from rest position, and the distance that the object traveled during that time. The total distance traveled is estimated to be about 1.25 meters. We can observe from the movie that it takes about 1.2 seconds for the hammer and feather to reach the ground. Our formula, which we have previously derived, is x is equal to 1/2 times g times t squared, which means that g is equal to 2 times x over t squared. Remember that this formula is valid only for when the initial position of the object is a rest position, i.e., the velocity and acceleration are both zero, which it is in this case. And so the value of g_moon that we get from the experiment is equal to 2 times 1.25 over 1.2 squared, which is equal to 1.7. The actual value of g_moon is 1.62. Possible reasons for the slight difference is uncertainty in the initial height, poor quality of the movie, and distance measuring errors due to the perspective view of the camera. Next we will use the individual frames of the movie to verify that the motion of the object obeys our equation of motion, x equals 0.5 gt squared, where g in this case is g_moon. There are 10 frames per second in the movie, and the movie lasts 1.2 seconds. And so we have a total of 12 frames. Currently we are displaying frame 0. We can measure the distance traveled by the object from the movie frames, and record this distance and time in a table, along with the theoretical values given by the equation x is equal to 0.5 g times t squared. We can then plot the experimental measurements of distance versus time, along with the theoretical value. We note that the two curves overlap, which shows that the motion of objects on the Moon and Earth follow the same law, except that the value of the acceleration of gravity is different. Press the next and previous buttons to go frame by frame, or press the play button to play the animation. When you would like to continue with the next slide, press the Resume button at the top of the navigation bar.